Thank you for coming to my poster, Emergent Dimensions Underlying Human Perceptions of the Reachable World. My name is Emily Josephs, and this work was done with Martin Habart and Talia Conkle. Explicit similarity judgments reveal the factors that shape how we reason about the world. One common view of the world is near-scale reach-relevant environments, like the tops of our desks or kitchen counters. We will refer to these kinds of views as reach spaces, and in this poster, we use judgments of reach-space similarity to infer the elements that shape our knowledge of the reachable world. What factors determine whether two reach spaces are judged to be similar? And what distinctions do people make among different kinds of reach spaces? Our approach was to capture the representational similarity space for 990 reach space images. Images were sampled from the reach space database. There were 330 categories with 3 images each. Behavioral similarity judgments were obtained in a triplet odd-one-out task. Now, it would be prohibitive to collect all possible triplet combinations, which would have required about 60 million trials, so we took a modeling approach. We had collected 1.25 million trials, then used sparse positive similarity embeddings, or SPOs, to predict the full similarity space from them. In our case, SPOs learned a 30-dimensional embedding. First, we validated this embedding by examining how well it captured behavior. Overall, the embedding correctly predicted 60.6% of trials in the testing set. This corresponded to about 82% of the noise ceiling, estimated by measuring inter-rater reliability. Thus, this model is quite accurate at predicting human behavior. Now, does the representational space derived from the model match the representational space underlying behavior? In a validation set of 45 images, the correlation between behavioral representational similarity matrix, where every triplet was sampled twice, and the model predicted RSM was extremely high at R equals 0.95. Overall, this gives us confidence that the SPO's embedding is an accurate reflection of human behavior. In the next 2 sections, we probe this similarity space to get insight into what shapes these judgments of reach-space similarity. First, we asked about the factors that might predict these judgments, specifically asking whether the location or function played a bigger role. Reach-space location was described at 3 possible levels: the setting, or broader environment type, the room the reach space is in, and the interaction locus, that is, the primary structure that anchors the reach space. Additionally, we considered the specific action that can be performed in the space. And we measured how well each of these predicts similarity by asking, given a reference image, which % of the time is a reach space that shares a label on one of these factors rated as more similar than one that doesn't? We find that while all 4 factors account for some of the structure and rating, action accounts for the most. This suggests that the reach space similarity is determined more by the action it affords than by the location it occupies. Next, we examined whether any interpretable clusters emerged in the space. How many kinds of reach spaces are there? Using k-means clustering, we found that a 5-cluster solution was a good fit for this data. In order to derive labels for the cluster, we first looked at the images in each cluster and articulated what they seemed to encompass. We validated these labels by asking participants to rate how much each image accorded to each rating, and then used the adjusted RAND index to assess how well the label captured the cluster. Overall, we found that there were clear clusters for reach spaces relating to food or electronic equipment. There were also less well-defined clusters for reach spaces related to storage, display, and retail, hobbies, crafts, and games, and chores or spaces related to liquids. One of the benefits of this model is that it summarizes the 990 image space with just 30 dimensions. Here we highlight 9 of these dimensions to illustrate some of the nuanced distinctions that they reveal. For example, separate dimensions emerged to indicate low clutter versus high clutter spaces, suggesting a role for visual features. Separate dimensions emerged among workshop spaces, separating spaces where you can make things with tools and those where the tools are stored, suggesting a conceptual division between active use spaces and passive storage spaces. The concept of storage also revealed complexity with separate dimensions for household, travel-related, and portable storage spaces. We also observed a division between familiar electronic reach spaces and those that require expertise to operate. Overall, the dimensions are interpretable and revealed further nuanced divisions among reach spaces. To conclude, we find that how we reason about the reachable world relates strongly to the things that we do there. This is reminiscent of the design stance that humans take towards objects, in which objects are primarily understood in terms of what they are for, and under which object similarity judgments are related to what they were designed to do. A similar stance has also been found with scenes, with similarity judgments relating strongly to the function of the room. This points to a larger picture where what things are for is a key component of what makes them similar to each other in their minds, and suggests that the design stance shapes our reasoning across a broad range of inputs and experiences. This large role of action also suggests that we can interpret the clusters we describe in terms of action-based differences. So through this lens, we see that food-related spaces involve ingesting things, and the action kinematics here involve hand-mouth coordination. Electronic spaces involve interacting with things that have hidden states, and the kinematics involve pressing buttons or keys. Finally, storage and display spaces involve short interactions with individual objects, and the kinematics involve looking at objects or grasping them with the hand. More work is needed to flesh out these action-related differences and to illuminate the kinds of informations that allow us to go from seeing something to knowing what it's for. Thank you for coming to our poster.